Fantastic. Well, good evening, everybody. My name is Harriet Brettel, and I'm the Exec Director here at the Keck Institute for Space Studies here at Caltech. It's my absolute pleasure and honor to welcome you here to the Ramo Auditorium for this fantastic public lecture that we're about to take on today. So before we do that, I've just got a few logistics things to mention. Please do turn off your phones, and we want to make sure that everyone is present and makes the most of the talk that we have today. And please do take a note of the exits that are around the room in case of emergencies. So I'm going to hand over now to one of our fantastic KISS affiliates, Maria Camarca, who is going to introduce our speaker for today. So Maria, over to you.
Hi, everyone. My name's Maria, and it's my pleasure to introduce tonight's speaker. Dr. Robert Pappalardo is a JPL Fellow and the project scientist for NASA's Europa Clipper mission at the Jet Propulsion Laboratory, California Institute of Technology. He has also served as the project scientist for the Cassini Equinox first extended mission at Saturn, for which he received NASA's Exceptional Service Medal. He received his bachelor's in geological sciences from Cornell University in 1986, and he obtained his PhD in geology from Arizona State University in 1994. His research focuses on processes that have shaped the icy satellites of the outer solar system, especially Europa, and the role of its probable subsurface ocean. Dr. Pappalardo has graciously provided a fun fact for tonight. During a Q&A in front of an audience of about 10,000 students, and without any heads up, Carl Sagan once used him as an example of a poor graduate student, doing what he does in planetary science because of love and dedication to the topic. So, to heal this memory, let's give a warm welcome to our speaker.
Thank you. I feel better already. Oh, it's so exciting to be here, and thank you all for being here. I want to introduce you, well, some of you know Europa, some of you might know Europa Clipper, but I want to talk about the star of our show, this amazing spacecraft that is on its way to an incredibly fascinating ocean world. So on October 14th, this happened.
Live at NASA's Kennedy Space Center for NASA's Europa Clipper mission, a nearly 2 billion mile, 5.5-year journey to Jupiter's icy ocean moon.
And liftoff. Liftoff, the Falcon Heavy with Europa Clipper, unveiling the mysteries of an enormous ocean lurking beneath the icy crust of Jupiter's moon, Europa.
Side booster separation confirmed.
Fairing is separated, and those will be recovered by SpaceX's own recovery ship, Go Cosmos.
This is a big moment for the program, for NASA, APL, and JPL. Let's watch.
Europa Clipper, separation confirmed.
And there you go. NASA's Europa Clipper probe, embarking on a long-awaited mission to study Jupiter's icy moon, Europa. And what a sight.
Now they wait for acquisition of signal.
And I believe we have it. Right. There it is. Confirmation of signal from the spacecraft, Europa Clipper.
Literally decades in the making, literally thousands of people's effort went into the success of that launch of the spacecraft of Europa Clipper. I started working on a science definition team appointed by NASA to define the science of a possible mission to Europa in 1998. And we've been iterating since then. This mission got the green light from NASA in 2015, and now here we are at its launch. But it takes 5.5 years to get there, so we've still got a wait to see Europa itself.
Live at NASA.
There we go. Okay, what makes Europa so special? Europa is one of the Galilean moons of Jupiter, first spotted by Galileo. Galileo, or first understood by Galileo Galilei in 1610. So there's an early sketch of Europa over 400 years ago from the Galileo spacecraft, named for Galileo Galilei, which orbited Jupiter from 95 to 2003. We learned most of what we know about Europa, the images that went into making this beach ball here. Europa is one of the 4 Galilean satellites. Io is the rocky innermost one, extremely volcanically active. Ganymede and Callisto are about half ice and half rock. And Europa is kind of a rocky world that is coated in a shell of ice and, we believe, water. The Galileo spacecraft made a dozen close flybys of Europa. Europa Clipper is going to make 49 science flybys of Europa at altitudes down to 25 kilometers off of the deck. And we'll talk about what it's going to do there. So Europa is about the size of Earth's moon, but it doesn't look anything like Earth's moon, which is covered with craters. Here we see a few craters, but not many. So here's one. These are not craters. So by the number of large craters, 10 or 20 kilometers across, on Europa, and we don't have all the surface image from Galileo, we can estimate the age of Europa's surface. A big crater like that should form about every 4 million years, and so the surface is probably about 60 million years old. Now, Europa itself formed with Jupiter is as old as the solar system, 4.5 billion years. So something in the last 1% of solar system history, since dinosaurs roamed the Earth, has repaved Europa. So Europa, we think, is geologically active today. Most of what you see here, the bright stuff, is ice. Those bright plains are crisscrossed by ridges and grooves of origin that we speculate about, we have models of, but we don't really know. There are a lot of models for how they might have formed. We'll take a look in a minute. And then that darker modeled stuff, called chaos terrain, is places where that old ridge terrain seems to have broken up. There's something warm in the subsurface that has breached the surface. What makes Europa so especially fascinating is that we're pretty sure there's an ocean down there. Again, the size of Earth's moon, but we think there's twice as much water in volume than all of Earth's oceans combined. It's smaller than Earth, but that's a thick ocean. We think something like 80 kilometers, what's that in miles? I don't know, 50 miles-ish. And on top of that, an icy shell, probably about 20 kilometers thick. We don't know for sure, but that's the best estimate. And then down there, rocky mantle and an iron core. What keeps Europa warm today when our moon is pretty dead, right? There might be a little heat down in the center. All the radioactive materials have decayed away for the most part. But what keeps Europa warm is tidal heating, something that's not going on today with our Earth and moon. So Europa, as it orbits, not to scale there in the upper left, gets a little closer and a little farther from Jupiter as it does. And it orbits every 85 hours, every 3.5 Earth days. It's going around Jupiter, gets a little closer and a little farther, 1%. And so Europa is being stretched when it's closer to Jupiter, stretched by about 30 meters, if there's an ocean as we think there is, and then relaxes as it's farther away. So this generates heat. It also nods back and forth a bit. And this makes heat within it, within its ice shell, to maintain a liquid water ocean. There might be some heat down in that mantle, but it's probably mostly in the icy shell. That's what powers Io's volcanoes too, is tidal heating, not an ocean, in the rock at Io. Okay, but why do we think there's an ocean today? Well, you can do the math of how much heating there should be from this tidal heating, and that says it should probably melt out an ocean, but do we know it's there today? Well, the Galileo spacecraft had a magnetometer and in a few flybys of Europa, noticed that Europa seems to have a little mini magnetic field, but that magnetic field moves around. Europa is orbiting Jupiter. Jupiter has an enormous magnetic field. If you could see it in the sky, it would be about the size of the full moon as seen from Earth in angular size. Enormously powerful magnetic field, and Europa is orbiting immersed in that magnetic field. And essentially, what the Galileo spacecraft was detecting is that Europa's magnetic field is countering Jupiter's magnetic field. Its little magnetic field is not stable, is not intrinsic to Europa. It's reacting, it's created by Europa moving through Jupiter's magnetic field. It's a little like if you have your keys in your pocket and you go through the airport metal detector, you're taking something that's conductive and moving through a magnet. And that makes a little mini magnetic field in your keys and sets off the metal detector. And that's what we think happened here. Europa is acting as a conductor as it moves through Jupiter's magnetic field. And what's that stuff that's conductive? A salty water ocean. The core is too far away. It's the ocean that is making that little mini magnetic field at Europa. So that's the best evidence that we have today for an ocean inside Europa today. And Europa Clipper is going to duplicate that experiment even better. So these are those ridges that we looked at, and here they are closer up from Galileo. Lower resolution data, higher resolution data inside of that, and we're zooming into one of these ridges, but it kind of looks like a double ridge, right? Most of the ridges travel in pairs with a trough, a depression down the center. To me, it seems like maybe something pushed up on the icy shell and broke it and moved the edges up as it did. So it might be something being pushed together, maybe it's something being pushed up. It could be back and forth motion, kind of like the San Andreas Fault, but instead of going all the same direction, moving back and forth creates heat, warms the ice, and may push these ridges. That warm ice moves upward and creates these ridges, we think, maybe. They might be sites of liquid water, and we need Europa Clipper to find out. There are also these bands, places where the surface has been paved over. And if you look carefully at this band on Europa, it's about 20 kilometers across. You can see a little ridge on one side and a little ridge on the other side. And if you were to take this apart in Photoshop and put it back together, that would be a double ridge. And lots of these older features that truncate at it, oh, that's a newer one, ignore that one, would come back together like puzzle pieces. So when this thing formed, that icy crust opened up, probably over the course of millions of years, and some material oozed out. So this is kind of analogous to plate tectonics that goes on Earth, but in Europa it seems to happen on the scale of these mini ice plates, happens differently. Wherever Europa's surface appears to have been breached in some way, it's dark and reddish. Okay, it's exaggerated a little bit, but it would look kind of an ochre color to your eye. And the Galileo spacecraft carried an infrared spectrometer and telescopes from Earth looked at Europa's surface in the near infrared, and they see these squiggles that, if you look at the bright stuff, are indicative of ice, and squiggles that, if we look at the darker stuff, are subtly different in shape and might be consistent with magnesium sulfate, Epsom salt, or sulfuric acid hydrate, battery acid. So this stuff might reflect the composition of the ocean, which could be a nice place to take a bath or something that's going to erode your skin. But a nice idea that's come up in recent years is, well, neither of these explains why these areas are reddish in color. But if you take, as Kevin Hand and colleagues did at JPL, if you take table salt, sodium chloride, and irradiate it with charged particles that are trapped in Jupiter, like the ones trapped in Jupiter's magnetosphere, what do you know? It turns kind of this ochre color. So maybe it's table salt or a mixture of these various salts. And Mike Brown's here somewhere who's done a lot of work in that area here at Caltech. But we're going to have an infrared spectrometer that's going to be able to tell us a lot more about the composition, the fingerprints of light reflected off Europa's surface, which tell us what that surface is made of. And we have other compositional measurements that we'll talk about. So this is the chaos terrain close up. Again, it looks like a bunch of puzzle pieces or like sea ice, but half the puzzle is gone. These blocks have just corroded away, if you like, probably related to a heat source from below, and some have cracked and some have moved around. Oh, I didn't have a scale on this one. There we go. Okay, so that gives you an idea of the distance. Used to be at Brown University. One of these plates is about the size of downtown Providence, for fans of Providence. Here's a nice model for maybe how chaos terrain could form if the warm ice, if there's a pocket of warm ice in the subsurface, then that can be heated enough. Actually, it was Dave Stevenson here at Caltech who promoted this idea at one point. I'm not sure if he believes it anymore. That tidal heating can concentrate in that warm ice and maybe melt out a lake within the ice. Well, there's a volume change in going from ice to water. The volume gets less, and so the surface would collapse over that, potentially forming chaos. So those are places where we might look for liquid water below the surface of Europa. And you're saying, how on earth are we going to do that? Or how in Europa are we going to do that? I'll show you in a minute with ice-penetrating radar. There might be active plumes at Europa. So fans of the Cassini mission and Enceladus know that Enceladus, a tiny moon of Saturn, has geysers, jets of water vapor that are streaming out of it. And there's been a lot of work here at Caltech, Andy Ingersoll working on that. And the idea is that cracks may be connected to liquid water and that material may be spewing out at Enceladus. Well, from Hubble several years ago, 2012 I think it was, there were observations of a glow of hydrogen and oxygen on the limb of Europa. And these Hubble observations measured this consistently over several Hubble orbits, so it seems to be real, but the signal to noise is very low. These are very hard observations to make. Maybe it's signs of analogous activity of geysering at Europa, but follow-up observations mostly have not seen anything. So we want to know if Europa really has plumes, and Europa Clipper will be able to tell if JWST doesn't find out before we get there. So far, James Webb Space Telescope observations say no, they're not seeing anything. Because if they are real, then, like Cassini could do at Enceladus, fly through the plumes, we could do the same and scoop up some of that material and analyze it with a very sensitive mass spectrometer, gas mass spectrometer that Clipper does carry, and a dust detector. So we want to observe, search for plumes with an ultraviolet spectrograph that Clipper has, and ideally fly through them or near them. So the big picture question for Europa is, if there's an ocean analogous to Earth, everywhere there's water, essentially, there's life, could there be life at Europa? Europa Clipper is not a life search mission. It is a habitability mission. What we're trying to understand is whether Europa has the so-called ingredients for life. Is there liquid water and where? Does it have the right chemistry? Does that ocean have the right chemical elements to build organic molecules? And really the hardest one, is there the chemical energy that could support life? At Europa, analogous to the seafloor of the Earth, life isn't going to depend on light and photosynthesis, although Earth's maybe a bad example because the ocean is connected to the surface, and so oxygen can get down to the bottom of the ocean at Earth. But on the Earth's ocean floor, in some locations, water interacts with hot rock and spews out material that we call, in these areas, we call black smokers. They're charged in reductants, hydrogen-rich material, methane, and at the base of the food chain are organisms that then these bigger critters feed off down at the bottom of the Earth's ocean floors. Could there be something analogous going on at Europa? Well, at the Earth's ocean floors, there's oxygen, as I mentioned, that comes down from the surface. What about at Europa? Well, at Europa, there is oxygen generated on the surface by the charged particles from Jupiter's magnetosphere slamming into the ice, tearing the ice apart into hydrogen and oxygen and leaving oxygen and oxygen-rich materials on the surface. If that stuff can get into the ocean, it can be a food for life. So we're going to, by understanding what's going on in the geology of Europa and by looking with radar as to how material from the surface can get into the interior and into the ocean, we're going to help understand the potential habitability of that ocean. Can oxygen-rich stuff, oxidants at the surface, get into the ocean? And do we have any evidence of reductants, hydrogen-rich material, essentially, down at the ocean floor? That's a hard one to do because we're not going to observe directly the ocean floor, but maybe we can get at the composition and infer what's going on in the ocean. So, as we turn to Europa Clipper here for the latter half of the talk, we have three main science objectives and one that's cross-cutting. We want to understand Europa's interior, and by interior we mean the icy shell and the ocean. How thick is the ice? What are the processes in the ice? How salty is that ocean and how thick is that ocean? And then we want to understand the composition of Europa's surface, its very thin atmosphere. We don't think of Europa having an atmosphere, but it does. 10 to the minus 12 of Earth's atmosphere, a picobar. It's enough that we can measure it with our very sensitive mass spectrometer. And also the surface, which we will try to infer how chemistry changes as it comes from an ocean to the surface as we understand the geological processes. But we want to understand Europa's composition and what that can tell us about the ocean composition. And we want to understand this bizarre geology, the chaos terrain, the ridge terrain. What's the relationship to liquid water? What does it tell us about the history of Europa? Has Europa been in a steady state for a long time? Did Europa go through a spurt of geological activity 60 million years ago and now it's kind of dead in comparison, which there are some models that say that could be true. So the geology can tell us that. We can tease that out by looking at broad swaths of Europa. I brought my little Europa globe here, and the Galileo spacecraft did an amazing job despite having a broken main antenna. And we had to broadcast the data down through something about 6 inches across instead at about 40 bits per second. So that's a couple of images per day. So about 10 to 15% of Europa was imaged with resolutions good enough to map the geology. Very few, you can count them on your fingers and toes, are super high resolution, like 10 meters per pixel. Stay. So by mapping Europa globally, we can put together the story of how old is this area compared to that area. Oh, okay, let me move on to activity. That kind of cross-cuts the others. Is Europa geologically active today, as we suspect it is? Does it have plumes, geysers there? What resurfaces Europa today? Is it formation of chaos terrain? Is it formation of ridge terrain, and then how does Europa fit into what we understand about other icy worlds and how they work. So here's our lovely spacecraft. Here's a little tiny model of it. You can come up and see afterwards. We are solar powered with 10 large solar panels. The total, let's see, let me give you something for scale first. That high gain antenna there, the big round bit, where we broadcast back the data from the spacecraft, is 3 meters across. That's about 9 feet across in diameter. So a person would come up, I forget, a third or half the height of the solar arrays there. It's about 100 square meters of area because light levels are low out at Jupiter. But yes, we can power a spacecraft at Jupiter, as the Juno spacecraft is powered now, that's investigating Jupiter itself. I mentioned the radar a couple times. There are multiple radar antennas. There are 2 HF, high frequency radar antennas, 17.5 meters long, that may be able to penetrate through the ice shell by broadcasting long wavelength radar. Ice is pretty transparent to long wavelength radar. So the idea is that it transmits a radio signal, long wavelength, and it penetrates through the ice, bounces off liquid water, which is very reflective to radar, and back to the spacecraft. So we're going to be pinging these radar as we fly by. And there are 4 other VHF antennas, which are very high frequency, so higher frequency, a smaller wavelength, and they may not penetrate as deeply, but will have a higher vertical resolution, so it can tell us if there are lakes within the icy shell. And I can tell you, Jennifer Dooley's in the room here. She can tell you about, there she is, about the engineering challenge of putting the radar antennas on the solar arrays, and why on earth did we do that? So that any electromagnetic interference from the solar arrays will be constant relative to those radar antennas. I hope it was worth it. The remote sensing instruments, as we call them, the things that look for at light in the ultraviolet and the visible and the infrared and the thermal, are all downward pointing toward the surface as we fly by Europa. So all the instruments could observe at the same time. Fans of Cassini will realize that not all the instruments could observe at the same time. We don't have the time to be choosing 1 or 2 instruments to do in a given flyby. It's a terrible radiation environment. If you walked out on Europa without a spacesuit, besides freezing death, you would be killed by the radiation in minutes to hours. And these particles are blasting our spacecraft too. So most of the electronics are in a vault, but the point is we don't have a lot of time for instruments to get radiation dose and not be used. Also, it's great for the science. We get all the observations at different wavelengths all at the same time. We can compare them really well. And the scientists don't argue about whose instrument gets to turn on, because we're all on at the same time, which is a really big deal. We had a sociologist work with us in designing the spacecraft team and the spacecraft. And then there's a couple of forward-pointing instruments, those mass spectrometers, the dust detector and the gas mass spectrometer. So we're flying into that thin atmosphere, and there's some dust in it from micrometeorites, and we can sample that stuff. And then we're not actually using the high-gain antenna for gravity. There are smaller antennas plastered around the spacecraft that we use for gravity, maintaining a link to the spacecraft, which is another way of telling us, confirming an ocean down there. And the magnetometer boom, the little tail of the spacecraft, which has the magnetometers, so we can do that experiment that Galileo did, but at much higher precision and many, many more times to get it, not just is there an ocean, but how thick is it, and what is its conductivity, therefore salinity, saltiness. So let me go through the science experiments. I alluded to most of them, but not all maybe. So we have the synergistic science, take all the data at the same time, I mentioned gravity, so we're tracking the spacecraft. It's about as sophisticated as my animations can get. As Europa moves up and down with a 30-meter amplitude, 60 meters for each cycle from crest to trough. And so these antennas scattered around the spacecraft. Then we have magnetometry, that's the magnetometers, to measure local magnetic field. We also need to understand the plasma environment, the environment of the charged particles around Europa, because they mess up the magnetic field. And we get good science by learning about the plasma too. But we need to understand the plasma environment to get at the magnetometry. So we have an instrument for that, plasma instrument. 4 sensors scattered in pairs around the spacecraft. Imaging, we have a wide-angle camera to get big swaths of the surface as we fly over it each time, and in color and in stereo. And we have a narrow-angle camera that from 50 kilometers altitude can get resolution of a 0.5 meter per pixel. Incredible over the ground track of the spacecraft. And that mechanism that's holding the narrow angle camera is a gimbal system. So it doesn't just have to look down toward Europa, it can look 30 degrees, up to 30 degrees in any direction. So we can target specific features as we go over, or we can look ahead and down and back and get stereo images in super high resolution, in color. The infrared spectrometer to look for spectral fingerprints at better resolution, both spectral and spatial, than we were able to with Galileo. Themis, that's our thermal instrument, and it will look for hotspots. Are there places that are notably warm? And Cassini, again, was able to do this at Enceladus, and therefore active today, and maybe a sign of liquid water at shallow depth. It can also tell us how blocky the surface is, which would be great for a future lander. I mentioned radar a few times to give us essentially like a CAT scan of the icy shell and what's down there, and where is there liquid water. Oh, and they're stored in little canisters here for launch and then deployed successfully recently. The ultraviolet spectrograph is our plume hunter to look for glow of the atmosphere, kind of like that Hubble image we saw. I mentioned the gas and dust mass spectrometers to measure the environment. And then there's the whole suite that works together, and the alphabet soup associated of the instrument names, that works together to give us this big picture of Europa. Here's some really cool pictures of the spacecraft being put together. In the upper left, you're looking into that vault. It's about 1/3 of an inch thick aluminum that contains the electronics of the spacecraft, of the instruments and the brains of the spacecraft, to protect it from these charged particles. Bottom left is the magnetometer boom being tested for its deployment, which was successful. There are 3 magnetometers. It's mostly the outer one farthest from the spacecraft that we use, but we use the others to understand the pollution, if you like, from the magnetics of the spacecraft itself. In the middle, before the spacecraft went into some thermal testing with simulators of the solar rays, because the solar rays were coming over from the Netherlands where they were being built. There it is in the lower right. There's a person for scale compared to those huge solar arrays. And in the upper right, a test of the spacecraft, and you can see the remote sensing instrument says like a big thumb is the narrow angle camera. That tells you where down toward Europa would be, and there's the high gain antenna on the top. The spacecraft thought it was flying at Europa. You do tests of checking out the systems, moving that camera around just as if we were making a flyby of Europa. Don't tell it otherwise. Here it was being moved into this space simulator, much easier said than done, because there were some issues. I love this picture on the left as it was being escorted into the thermal vacuum chamber. So they pump down, pump the air out, and then make it warmer as equivalent to how close to the sun the spacecraft will get, because it'll be about twice 2 suns worth of heating, and then the cold of the Jupiter environment. The solar arrays were integrated to the spacecraft at Kennedy Space Center, but first the radar antennas were attached before the spacecraft got there. So here it is departing JPL, and my wife and I then chased it down the 210 for quite a while until we were satisfied to let it go to March Air Reserve Base, where it was flown on a C-17 to Kennedy Space Center and their payload servicing facility. And then the solar arrays integrated onto the spacecraft and tested there at Kennedy Space Center. And it was encapsulated into the SpaceX fairing, one of the last pictures before we got to see it deploy from those cameras that we saw in the beginning. And on the right, it was very exciting to be there as it paraded out of the payload servicing center in its fairing and over toward the launch hangar, SpaceX launch hangar. And it was multiple hours. So I was in the parade for maybe a half hour before I'm like, okay. But it was very exciting. And then launch on October 14th. I'm skipping the part about the delay thanks to Milton, the hurricane, including the tornado that hit our hotel that night before Clipper was supposed to originally launch, but it was a beautiful day after Milton passed that we were able to launch on the 14th. Ruined our party, though. Okay, so on the left, you're seeing the interplanetary trajectory, how we get from Earth to Europa. And this has been updated for our launch date of October 14th. And then we're going to make a gravity assist of Mars on the 1st of March. So we're booking it to Mars, getting there in 4.5 months total. We're going to do a calibration of the thermal instrument. When we're there, about a day out, we'll see Mars. And we're going to do a test of the radar as we fly by Mars as well. And then we come back around and make a flyby of Earth, because these flybys are gravity assists to gain speed to get out to Jupiter. So it's faster to do that than to go directly. And we get to Jupiter in April of 2030. It's then about another, I think it's 11 months before we make the first flyby of Europa. But time passes. Here's a cool animation of, let's see if it works. There we go. Of Clipper getting to Jupiter and first making some long looping orbits. We have about, I think it's a 7-hour burn when we get to Jupiter of the engines. And then we come into an orbit where we get into a resonance with Europa, where it's a 6-to-1 resonance. Every time Europa goes around 6 times, here comes Europa Clipper again. And then we'll change the orbit and make flybys of Ganymede and Callisto to do that, and encounter Europa in a different place in its orbit. And now with a resonance of 4-to-1. Every time Europa goes around 4 times, here comes Europa Clipper. So we'll know what we're doing by then, be able to do it faster. So in the first case, we see the hemisphere that faces away from Jupiter as Europa orbits fully lit. And in the second half, we'll see the hemisphere that faces toward Jupiter fully lit. And that's why this complicated, interesting pattern, which gives us this kind of web of flybys. So we're orbiting Jupiter, but we wanted to, as best as possible, simulate orbiting Europa. That is, fly by Europa from different perspectives to see as broad a range of latitudes and longitudes as we could. You can see the flybys, the closest approaches, the warm colors are concentrated in the places toward and away from Jupiter. Here comes the big guy, there it goes. So here's the hemisphere away from Jupiter. Like our moon, it always faces one side toward the parent planet. And most of the flybys are in the hemispheres toward and away from Jupiter. Because we're a flyby mission, we can't make a close flyby on the leading or trailing side, or else we'd be flying into Europa or out of Europa. We can't do that. We can't crash onto Europa. Planetary protection would not permit that. We don't want it. And on the right are samples of potential coverage, again, warm colors being higher resolution from the various instruments. Whereas for the radar, it's the crossing points of the flyby trajectories that matter. So why are we doing all this? Europa is an amazing place in terms of geophysics and geology and chemistry and even atmospheric science and plasma and magnetism. But we're going to understand, could Europa potentially be an abode for life? And because it's an example of an ocean world, we think, in our solar system. Really, that's a new class of object that, 20 years ago, when Carl Sagan was pointing me out in the crowd, it seemed such a long shot that Europa could have an ocean. And now we're pretty sure, by understanding better the physics of ice and what's called convection, the stirring of that ice, kind of like a lava lamp, and from what we understand from the Galileo mission and Cassini, that Enceladus and at Saturn and Titan at Saturn and Ganymede and Callisto at Jupiter and Triton at Neptune probably all have oceans within them today. And that's just amazing. We're used to thinking of the habitable zone, thinking of ocean worlds with an exposed ocean. Dave Stevenson has made this point in the past, but Earths are probably relatively rare out there beyond our solar system and other solar systems, whereas icy moons of giant planets are probably common out there. And when they are in these resonances that keep their orbits eccentric and allow for tidal heating, they may have oceans within. So we're exploring a new class of world as to whether they could be habitable environments and to understand how they work as worlds. And that's an amazing place to be. That's going to be the incredible legacy of the Europa Clipper mission. Following is the Dragonfly mission, which is going to go to Titan, and it launches, I think, in 29 or 30. They just announced that'll be in a Falcon Heavy to explore Titan and understand the organic materials known to be on its surface. So we really are setting sail for ocean worlds. And I want to finish with an exciting piece of our mission, literally, of our spacecraft, which was originally dryly called the vault plate, but was branded by the engineers who assembled the spacecraft as the poem plate. You can see one side of it there. I'll describe both sides of it here and why it's called the poem plate. So on the top left there are the sounds, are the waveforms made from saying the word water in 103 representative languages of our planet. This isn't going to be found by Europans, right? That's not why we're sending it. It's not like the Voyager record or the Pioneer plaque that might be found by some civilization someday. Well, really, those two are messages to ourselves, but this we know is a message to ourselves. And we wanted to convey to the public that this mission is kind of joining Europa and Earth in understanding another water world. And that is so well represented by the poem that is inscribed here on the poem plate by the poet laureate of the United States, Ada Limon, who agreed to write a poem that would be inscribed and was co-signed by 2.6 million people who are sending their names to Europa on the poem plate. and I'll say more about that in just a minute. There's a representation of a bottle in a sketch of the Galilean satellite system. There is in the very top the Drake equation, which Frank Drake used to describe how many habitable worlds may be out there. And Europa Clipper will help contribute to a couple of those terms. There's a portrait of Ron Greeley, who led several of the Europa science definition teams, happened to have been my thesis advisor as well, and passed away several years ago. So he'll be riding with us to Europa. And after we're done here, I'll start by passing this around. This is an exact replica of the plate. This was our essentially test model of this engraved plate. And this one, unlike the picture, because this is newer, or it was added newly, contains a replica of that chip with 2.6 million names on it. And not encoded in the chip, etched on the chip. So good enough microscope, you'll see the names. So let me pass this around a bit. I forgot to mention the center of the side with the water words is a symbol which is a Fourier transform of the American Sign Language symbol for water. So we were thrilled to have a partnership with Ada Limon and the Library of Congress in this adventure, in this exercise of putting together the poem plate. And I want to leave you with Ada Limon reading In Praise of Mystery, a poem for Europa.
In Praise of Mystery, a poem for Europa. Arching under the night sky, inky with black expansiveness, we point to the planets we know. We pin quick wishes on stars. From Earth, we read the sky as if it is an unerring book of the universe, expert and evident. Still, there are mysteries below our sky. The whale song, the songbird singing its call in the bough of a wind-shaken tree. We are creatures of constant awe, curious at beauty, at leaf and blossom, at grief and pleasure, sun and shadow. And it is not darkness that unites us, not the cold distance of space, but the offering of water. Each drop of rain, each rivulet, each pulse, each vein. Oh, second moon, we too are made of water, of vast and beckoning seas. We too are made of wonders, of great and ordinary loves, of small, invisible worlds, of a need to call out through the dark.
Here are some ways to get involved and follow Europa Clipper. Thank you all for being here. I'm happy to take some questions.